that. So this guy, I think will tell me whether the interrupt service routines or where that information is. Paging modes, page fault, protection, interrupt and exception handling. Here we are. Got a feeling interrupt stack table switching IRET stack frame maybe. No. Error code tasks. Masking instruction breakpoints, NMIs, hardware interrupts, machine check, software, program error. Where would it be? Maybe this? Uh, 64-bit mode also pushes the stack segment stack pointer unconditionally rather than only on CPR change. Push it's fixed at 8 bytes. Oh, hi, Chili. Glad you could make it, buddy. How's it hanging? Oh, there we are. Stack pointer after transfer to handler. This is perfect. I think it's this. So 4 bytes, the CS error code, legacy mode, 64-bit mode. So we get error code, RIP, code segment, R flags, stack pointer, and something segment. Wonderful Sunday. Yes. I managed to fix the HP ET woes that we were having last night, and I was doing something really dumb. So I was getting bitten by pointer arithmetic, or specifically scaling pointer arithmetic, when I was calculating addresses. And then my other really big problem was not marking volatile where needed. So now there's a lot more volatile keywords around this code because it's dealing with all memory mapped IO. So given that we've got the sleep working perfectly, it sets us up into the position of being able to time the per core timers. So this HPET is literally just a support timer for you to measure the timers that exist on each core. And then once you've got the measurements done for each core, you then work based off those local core timers rather than this heavy, high-performing timer. So I want to do that today. But I've just taken a small side quest into handling faults a little better. So I at least want to get the error code off the stack when we land in the ISR. And I've just woken up my Alexa. So yeah, I'm going to try and extract the error code because I want that for the logs. So at the moment, when I generate a fault, I don't know why it faults, and that's kind of crappy. So we just at the moment get a unhandled fault occurred, but I want to be able to map that to knowing exactly what fault we received. So I'm going to do that. So that's a cleanup exercise. And then once I finish doing that, we'll get onto the LAPIC timers. And then once we finish the LAPIC timer, which I think will be quite easy because I've already got part of that code working. I just need to plug in the measurement code. I then need to begin, and I think we're going to start this today. We're going to look at reading a FAT32 file system. So we want to be able to read and write to a hard disk. And that journey is an interesting one. We're going to scan for devices that are connected on the system. We're going to look and find for storage devices and then start talking to them. So you'll get to see, hopefully, which detail we go to being able to talk to drives. So they talk based on partitions and sector numbers, I believe. They don't care about your fancy file structure that you have in a virtual space like Windows or Linux. So we want to be able to read and write FAT32, and that will be amazing because then what we can do is plug that into our console. So we can expose the devices to the console and we can start navigating through the files. But ultimately, I want that unlocked. So I want that huge milestone unlocked of being able to look at files because I want to be able to install user applications into the operating system. And then start thinking about running programs on the different cores that we have. So we'll write a hello world user space program. We'll install that into the OS image, and then the kernel will pop open the drive, find that installed program, if you like, and then load it into RAM and execute it in user mode. So yeah, lots of really cool, juicy stuff. And given my experience yesterday, that lost time, it's not really lost time, but I'm glad we went through it. I'm glad we had a problem with the volatile variables, and I'm glad we had the problems with understanding scaling pointer arithmetic because now I'm kind of seasoned into knowing how to deal with memory mapped IO. Like I've been bitten by every freaking bug that you can possibly run into with the most weirdest side effects. And I'm just glad we've had that experience. So we've leveled up in lots of things. Like I understand in the assembly now, like what these numbers here are. These are the instruction codes and the opcodes, which are, this is the human readable assembly instruction, but this is the bytecode that is sent to the CPU so it knows what instructions to run. Now, that's important because if you're going to write a compiler that produces assembly, you need to know how to map to these opcodes and these instruction code IDs. So yeah, lots of awesome knowledge being gained. It's a pretty exciting roadmap. Really, lots of exciting stuff coming up, and I'm hoping it's going to get faster now. Hi, Fly. How you doing? Before I do start cracking into the code, is my microphone feedbacking like it was yesterday? Because I've tried debugging it with recording and playing back what I'm doing, and I can't find anything wrong with it. So let me know. Do, do, do. Hope you don't mind the piano in the background as well. I've been told in the past that piano music and my voice combined is like a sleep drug. So I've got to be careful not putting everybody to sleep. Okay, so let's get cracking. So we just dug open this beautiful picture, which is what I was after, and I can see that the stack pointer is looking directly at the error code. And how I'm reading this is at +8. You get the instruction pointer and another pop off the stack. You'll get the code segment, and then you'll get the flags, and then you'll get the RSP, and then the stack segment. But this is a bit of a fuck around and find out kind of thing. So it's a bit of assembly that I've not really done before, and I'm hoping that it all works out. So the plan of action is going to be, we're going to pop the stack into a general purpose register. We're going to move that value into the parameters in registers, and then hopefully catch that in the handle fault function. So that'll be a pretty cool step. So what I need is a reference to the assembly 64-bit registers for function params. Calling conventions, alignment, parameter passing. Funny enough, I've landed on Microsoft's site for this information. But it's kind of, this is what I was after. So integer valued arguments in the leftmost 4 positions are passed in left to right order in RCX, RDX, R8, and R9 respectively. And the 5th and higher arguments are passed on the stack as previously described. Floating point values, which we won't have. They're also placed in the integer registers. Okay. Strings are never passed by immediate value. Instead, a pointer is passed to memory allocated by the caller. Strings, structs and union sizes of 8, 16, 32, or 64 bits. Passed in as if they were integers of the same size. Okay. So RCX, I'm wondering then if this is just a simple pop into RCX to get it into the handle full. Right. Again, new stuff here. So get the full vector code. And now the signature on this changes. So is it as easy as doing this, I wonder? So vector send D, and then it'll be that vector code we just grabbed. Such dramatic music behind, seems like you're decoding Enigma. Yeah. It's my piano playlist. Music to code by. Let's try this one. Could be even worse. It might be like spacey sounding music. Okay, so now we've got that in place, right? So we've got this fault stuff. We need to kick the tires and generate a fault. How are we going to generate a fault? We can generate an int3, which is the debugging interrupt. So we'll do that in the kernel on boot. I guess we'll just do it here. So this will cause that'll cause a fault. And then fingers crossed in the log we see the vector. If it just works, I'll be so happy because then it's all my theory. Kicking in, but did we get a bad compile? Try again. Undefined reference to handle fault. Extern handle fault. Did I not save that? Oh, I've called it faults. But rightly so. It's just handle fault. Oh, there we are. So there's the fault, and we got a vector number 0, which I don't think is correct. If we look at the exception codes, which is down here, I think. Vector number 1 is the debug vector number. Floating point error, machine check, SIMD, divide error, stack fault, general protection, control protection. What I need is a way of generating two different vector faults. So I wonder if I can generate a divide by 0. I think if I remember, trying to do a divide by 0 is a pain in the butt because GCC protects you from it. So let me throw this at ChatGPT and see if it can recommend. So, oh, we can produce a segmentation fault, right? I just thought if I can, yeah, let's just initialize a pointer to somewhere random. Oh, there's also this one, built-in trap. Generates an undefined instruction exception on a 64-bit processor, UD2. Try this one. Let's kill that. Yeah, I think the hardest part of all this from me trying to generate exceptions before was GCC likes to fight you. But so we've generated the fault here. And if I look at this fault that's generated in the QEMU log, I've got a vector code of 6, which does not look like what we have in the handler. So let's step back with the debugging and let's try and just pass in a fixed value. So comment that out. If I move, I don't know, this value into RCX, will it let me do this, I wonder? We've possibly just faulted inside of a fault. I'll tell you what I'll do is we'll check how Live is doing this. So I just want to make sure that RCX really is what I think it is. So in here, oops, I need to open this in code so I can navigate better. Okay, so does it do anything with RCX other than pushing that register? Stack pointer. And then call whatever was placed into BX there, which is the address of the thunk macro. I guess I can just ask ChatGPT, right? How can I pass parameter to a C function when calling it from assembly? bring this over so you guys can see it. What I'm doing with this example assumes the use of the C declare calling convention, which is common in GCC and CLang on 886. Parameters are pushed onto the stack in reverse order, right to left, and the caller cleans up the stack after the function returns. Oh, interesting. It's referencing Linux. But that's kind of in the context of Windows and Linux. Calling assembly from within a C program using an inline assembly can be a bit simpler as you can let the compiler handle some aspects of the calling convention for you. I mean, we can try doing that, right? We can try. Let's try RDI. I don't know if I can do that though. Can I just move a decimal into that location, I wonder? I have to check the log. Let's see if it. Yeah, it's not getting that far. I think I'm maybe blowing up on this line. Which then I wonder if I can just do this. Try it that way. All right, we've got a number, but it's minus 214 million. So we're kind of getting somewhere. Oh, have I got the syntax the wrong way around? No, because then Lyra would be doing that same thing, right? I mean, I guess I can just try and flip them. So that one just like hard crashes. So how about this one? That one hard crashes. And I'm getting vector 8 in that debugging. Where's the exception list? Do, 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 do. In the TOC. Oh, interrupt 8 is the double fault. That's when you fault within a fault. So I've got to keep remembering that. When you fault within a fault, you're going to see VO8. So O and E was the first one. If I'm not mistaken, there's a hell of a lot of them. Did it just mindlessly blow up like a million times trying to handle the fault? So E would be what? 14 page fault. Why? Why did it not halt though? Curious. But it lets me pop into RDI, which is the weird thing. Yeah, I do believe this is a wrong way around. It's source and destination on that move instruction. It's not the other way around. Sometimes when I Google, it's actually given me destination and source, but there must be a different. So we got a massive spam again of so we double faulted here. And then we got this general fault here, but why did we get so many? Like 1,000. Seems wild. And I think it's definitely this line that's killing us. Why? Yeah, so that generates that single exception there, vector 6. Can we see what the stack pointer is set to? Maybe it's something we can work with. Wait. Wait. I just want to try something. I want to see if that comes through automatically. It might do. Thanks for the follow, Swills. Made me jump, I was so focused. Okay, so we're faulting, we're not getting a value, so it's not automatically picking up that vector from the stack. And it's definitely got something to do with pushing into RDI. But we just don't know how to manually get a value on there. So tell you what we'll do. Let's no, because if we push stuff, it means we'll lose what's already on the stack. Or, okay, let's leave that as a 64-bit value. Let's pop that vector again and see if that makes a difference. No. We are getting something, but it's not. You know what? I'm going to just do a couple of pops. It might not be where I think it is. There we go. That says vector 8, and it was 6 that got thrown. So we're not quite there. But we've got a number now. Okay, can we pop again? I bet the order that I'm thinking of stuff is reversed. 642. Okay. How about again? We'll keep going until we get to the vector number we're after. Okay, that's a huge number. God, this is really, fuck around and find out kind of process. Vector 16. And again, nope. We want 6. That's 0. I wonder, are we popping 64-bit values? 0. I've got a feeling there's nothing left for us for walking up this stack. There's another big number. Five, 5, 3, 5. Gosh, how big is this stack at this point? All right, this strategy is not working. So I'm gonna have to Google. I don't even think GPT can help me here. When I attempt to write to the RDI, I generate a page fault. Why? If RDI is used as a pointer to a memory location, and you attempt to write the memory address in RDI, a page fault will occur. Ensure that you've got memory access using the RDI as a pointer is valid and permissible. I mean, it's got to be if we're popping into it. Permissions and mapping. And looking at Lyra OS, so they are setting RDI here to the number, like their interrupt number. What does this line do? Load effective address is used to put the effective address of the operand into the specified register. The instruction you mentioned is using the layer instruction to commute the effective address of a label. Oh. And it loads the address into RBX. Interesting. But coming back to our RDI point here, it is just moving a value into RDI. Why can we not? Why can we not write that register? Let's go westdev. x86. This is a common process for me in OS development. A series of resources that I have to walk down. Oh, it thinks it's a memory reference. I need to use $. Oh, that works. Okay, cool. So that proves now that we know how to pass parameters over to a C function in assembly. So we're using the RDI register. And now all that's left is knowing where we get the interrupt vector from? Which I believe, looking in the software development manual, so the key to this is somewhere in here. Error code. Can it be that? When an exception condition is related to a specific segment selector and IDT vector, the processor pushes an error code onto the stack of the exception handler. Right. The error code has the format shown in figure 6.7. ext IDT TI segment selector index. External event bit 0. When set, indicates the exception occurred during delivery and event external to the program, such as an interrupt or an early event. The bit is cleared if the exception occurred delivered, blah, blah, blah. Index portion of the error code refers to a gate descriptor in the IDT. When clear, indicates that the index refers to a descriptor in the GDT or the current LDT. Is this the same error code that I'm wondering about here? When clear, it indicates that the index refers to the descriptor in the current GDT. Okay, 64-bit exception and interrupt handling. 64-bit mode, interrupts and exceptions similar to what has been described for non-64-bit mode. The following are the exceptions. 64-bit code, the size of interrupt stack pushes is fixed at 64 bits. The processor uses 8-byte 0 extended stores. The stack pointer is pushed unconditionally on interrupts. In legacy modes, this push is conditional and based upon a change in the CPL. Direct behavior changes as a new interrupt stack switch mechanism. So I wonder then, is it stuffed somewhere in the 64-bit value? Is that my problem? Another thing too, though, how am I getting a negative? So when I pop the RDI, going back to this code now, there's no I should be getting a negative on that vector number. That is a bug in itself. Oops. LD, LU. It's the same. UL L2A convert 60. Oh, that's signed. So it's LU that I need. Okay, that's a large number because that's a lot of bits that are turned on. If we wanted to, I do believe in my string package, I have a nice print binary 64. Buff must be at least 72 bytes, so I can do in the IDT, where are you? Boop. Let's just get a 100 byte buff and then let's pass in that buff, pass that value in. We'll do %s and then we'll pass the buff in. All right, so now we've got a binary view of that pop. So I want to see, now that I can see that, does it relate to any of these diagrams? So IDT gate descriptors, it won't be that one. Error code. That's a 32-bit value though. Shadow stack ESP after transfer to handler, before transfer to handler. To return from an exception or an interrupt handler procedure, the handler must use the IRET or IRETD instruction, which we're not. We're halting the kernel because we don't care to resume after catching a kernel fault. I've got a feeling it's right here in front of my face, but I'm not interpreting the information. The processor performs a call to the exception or the interrupt handler procedure. The SSP is saved to the model specific register, which we're not doing. We're not doing any privilege level switches here. So we're on this one here. If the procedure is going to be executed at the same privilege level, and shadow stacks are enabled at current privilege level, the processor saves the current state of this code segment, the LIP, SSP registers on the current shadow stack. Shadow stack usage on transfers. Pops the top of the stack value. This is prior to the interrupt. Flag use by exception interrupt handler procedure. Interrupt tasks, which I do not believe we're doing. Descriptor privilege level, offset to procedure endpoint, segment flag, IST. It's a gate descriptor. Stack frame. Talking about IREP popping, but we're not getting that far. Why? Where are you, vector number? Wait, shouldn't we be able to gauge this from Lyra's source code? Macro interrupt number push 0. Okay. I'm wondering. I don't feel like I'm getting anywhere. The following section describes conditions which generate exceptions and interrupts. They are arranged in the order of vector numbers. Like, what I'm doing is probably super common, right? Would help if I tell it x86. There we go. When an interrupt is triggered in protection mode on it, is it possible to figure out what the interrupt was fired? For example, let's say I called int OFF. In the handler, can I find out that int OFF was called? Oh, you know what I've just realized? Oh, I'm so silly, actually. When I have, man, I've just realized why it's not clicking. Because when we set the gate here, I'm setting all of the interrupt vectors to a single function. By the very nature of setting those vectors all to the same function means that I can't determine the vector number. Which is exactly what this just made me think about. The ISR addresses are stored in the IDT, so that's a place where the differentiation starts. There's no very good alternative to unique ISRs. Here's why. In ISR, you could examine the caller stack, see the return address, and examine the code right before the return address to see if it's the 2-byte int instruction. The problem is there are also int3 and int1 byte instructions. Could be anything before blah blah blah. You should keep in mind that exceptions aren't handling in the exact same way. Some of them come with the extra information saved by the CPU on the stack prior to entering the ISR. It's the error code. Others don't have this error code, and your ISR needs to remove it before doing an IRET. A mistaken determination of the exception vector will crash or hang your code. Now, about hardware interrupts. You may be able to determine which hardware interrupt is being serviced. The PIC has the in-service register ISR. For a bit set to 1, as far as I can remember, indicates the IRQ. But if you let interrupts of higher priority preempt ISR handling interrupts of lower priority, then the interrupt identification quickly becomes more complicated than necessary. So just go with unique ISRs for all of your IRQs, exceptions, and system calls. Or use one common ISR but with multiple unique entry points, each saving a unique number on the stack, which is what I believe Lyra's doing. The common code afterwards will extract this number and do what's necessary for that interrupt vector. Right. But it's kind of cheaty looking at Lyra doing it. Like, I don't think I can achieve what Lyra's doing because I don't understand its macro. So it kind of explains though what it's doing at the top here. This push is saving the vector number on the stack. But it's doing it very selectively, and again, I don't know why this logic exists, but I think, like, what's so specific to 8, 10, and 11, and 12? Let me just go check what they are. Double fault, segment not present, stack fault, 13, general protection, 14, page fault, 17. Okay, what should we do? Multiple entry points per ISR. So it sets up an array of ISR thunks, which is being defined in here. So that blows my mind straight away. How have you managed to wire up an array? A line in 8 bytes. ISR thunks is the label. Set I to 0, repeat 256 times. Thunk address I. Yeah, I don't think this is going to be as easy as I thought. Let me just let's see if ChatGPT can explain this code. Global symbol, okay. Align 8. Aligns the next data instruction on an 8-byte boundary. Okay, this is a label marking the start of the thunks table in memory. How is that a table? Labels in assembly serve as markers or pointers to particular locations in the code or data sections, allowing for easier reference and manipulation. Oh, so section data. So this is a data declaration. Oh, I see. Sets a symbolic variable I to 0 in assembly language. Set is used to define constants or symbolic names for values. Here it initializes a counter I that would be used to iterate through ISR thunks. I see, so that's the index of the counter. Interested to know what that line's doing. Yeah, repeat the enclosed part 256 times. Okay, so this line is meant to be a placeholder for an actual instruction or macro that generates or references a thunk address. I is used to interpolate the current value of I into the instruction. So that is this macro. So what does quad do? Interrupt thunk num. And in summary, the script generates a table of 256 ISR thunks with each entry in the table being aligned to an 8-byte boundary. Each thunk is like a small piece of code that helps in managing or dispatching interrupts to the appropriate handlers. This specific operation of thunk address and how it uses the index I would depend on the rest of the system mechanism. Okay, let's explain the macro. We might be able to get to a point of doing the same. Okay, so defines the macro, and macro is assembly powerful. That's the definition. Blah, blah, blah. Yep, lovely. This line starts the definition of macro name thunk address. So takes a single argument num. The argument num is intended to be a numeric value that we use to generate a unique label or identifier in each ISR thunk. So like the macro, this line generates an instruction to place a 64-bit quad word value in the output. The quad directive is used to define a constant value or address that occupies 8 bytes of memory. The value interrupt thunk num is intended to be a label for an interrupt thunk function where num is replaced with the actual numeric argument passed to the macro. It effectively generates a unique label for each thunk based on the num argument. For example, if num is 1, the label would be interrupt thunk 1. When the thunk macro is used with a specific number, it expands to a line of code that places the address of the corresponding interrupt thunk function in the output. So invoking thunk address 5, you would get quad interrupt thunk 5. Assuming such a label exists elsewhere in the code and refers to an actual interrupt handling function. All right. So that makes sense. I get what that's doing. So that is producing an entry in the data section. Thunk address. Oh, and then we've got a thunk macro. Interrupt thunk num. Oh, it's generating a label. Oh, right. It's spawning 256 labels. It's like copying and pasting this entire code block 256 times. Which is what this text section is doing. Holy moly. And then this global entry is something else to do with API. I forgot what that is. Is that an interrupt specific to the processor, I think? Panic CPU counter. Yeah, I think that's a CPU specific panic, which we don't need to concern ourselves with yet. So that spawns 256 copy and pastes of this code block, generating a label that you can jump to for the interrupt number. And then we're writing in the data section the addresses of those labels, which then flow into this array here, which then it iterates and attaches each generated macro into the IDT table. That's pretty nice. That is very nice. And in simple words, yeah. I've never done assembly to this level, so it's entirely learn by example. So everything I see that this operating system is doing is just like, once I've learned it how to do it cleanly like this way, it's going to end up me copying what they do, but I don't know any better. Does that make sense? Like, what I understand in my operating system, that to get a unique internet in an interrupt service routine handler, I would need to write 32 fault labels in here. Like, I'd need to write ISR handler fault 1, ISR handler fault 2, but all the code will be copy and paste. So using assembly macros, I can expand using a for loop and generate code blocks. But what I didn't know what we could do was pass in a section data. So this is the magical thing here, that you're defining a data section, and this quad instruction in the macro that it's writing out the addresses of those labels. It's such a clever mechanism. Like, I love what it's doing. I think I'm confident enough to know that we can do this ourselves and probably get to reporting on the vector number. Or can we? Oh, I know what's happening. I think I know what's happening with this push 0. It's pushing onto the stack a made-up error code for those vector numbers. So what it's saying that if I'm not in this list of vector numbers, I don't have an error code. But I'm going to push one onto the stack anyway to provide one. Okay. Interesting. See, I wish this was commented. When I do it, I'm going to comment the shit out of what I'm going to do because it's learning, you know. I won't need this because that's user space detection, and we're not in user space yet. So all I want to do is set up a bunch of 256 interrupt handlers, and when that handler gets generated, wait, that doesn't explain how you get the vector number though. So, oh, but you have it in the macro number. Oh, it's here. So you're writing the number of the macro into RDI as the first parameter, and that's how you get it. Oh, great. And then it's saying here, if it's a user-generated IDT, it's going to do an IREQ. If it's not, it's going to perform a swap GS, which I don't know what that does. Okay, so let's just try and do a really basic generation of, you know, what does alt macro do? Does that mean that it's a macroed file? Is that what it is? See if I can search for that. Alt macro. Oh, right. So it's in a macro mode. Okay. Puts the file in macro mode. All right. So let's think about this. We're going to write a macro that generates 256. Do we want to do 256? I'm going to do 32 for now. I just want to get the faults handled. Because for the faults, I don't want to do anything fancy right now. I just want to dump in the log what the fault code was. Damn, this music. Can you hear it? It's so dramatic. So dramatic. All right, let's do this. All right, let's do this. All right. So we're going to go into macro mode, alt macro. Then we're going to generate a macro. I guess we'll use the same naming conventions because it's quite common in the OS community to use this convention. So here's the macro. And then we're going to generate a function called interrupt thunk underscore with the parameter name on it. So hello, Neg. How's it going? The music's great. Dude, it's getting me pumped. It's got me into like such a serious mode. It's like I'm saving the planet or something, you know? Okay, I'm not going to bother doing this number checking because I don't fully understand it, right? And I'm never going to copy and paste some stuff that I don't fully understand. So let's now. So we're in. So we're in the macro. And we're going to generate some code for the macro. And the generation for this code is I want to move. How do we move the number? There's a syntax problem. So it's $. So it's \num that does the rewrite. So I want to move that into the RDI, which is the first parameter. Let's comment this. Move the macro or the macro param number into RDI or vector number. Okay, and then we're going to do CLB, which yeah, okay. And then we're going to call wait, hold on a second. No, yeah, this will work. Call handle fault. I'm not doing this fancy stuff here because I don't know what it's doing. Oh, it's jumping to the specific location of the label. Maybe. Instruction pointer. What is it doing there? It's calling into the specific label. For the ISR. I can't quite grasp that, but it would. Is this going to work? Do I need a macro here? All right. Something not clicking right just yet. So we'll forge forward. So we're halting the CPU. It's because we don't care, right? Now, ISR handler faults. So this goes away. That doesn't exist anymore. We do need to end the macro though. With an end M. Okay. Can I indent that just to kind of... So this bit is the bit that's a bit hazy to me. So we've got a bunch of addresses. So this macro is going to write the interrupt labels. So this is what's connecting the labels to the array. So in that macro. And now this is where we're generating a data section. We're exposing the label. God. We're doing 8-byte alignment. And now we're generating this code. And this is where it gets funky. So we're defining a variable. We're asking it to repeat 32 times. Because I only want to grab 0 to 31. We're going to call the macro thunk address, passing it the parameter of I in the count. It's going to generate the label address. Right, okay, that makes sense. But then how does this get called? Global. Oh, you know what? It doesn't make sense. This is not a function, this is a data table. Okay, that makes sense now. So then we increment the I counter and then we end the repetition. All right, so that generates the array. Now, in the text section, which is the generated code section, because all we've got is a template up here, so we need to generate the code blocks. So again, we're going to do another for loop. We're going to repeat 32 times. We're going to call the thunk macro to bring the code in for this number, and then we're going to increment. All right. Let's get some comment in here. So generate the interrupt handler code from the macro vector. This up here is generate the data table containing the label addresses, the generated labels. And I think that's it. This goes away. So all that's left now is, it's going to be kind of lame calling that with capitals because that's going to land in code. So we'll lowercase that as well. Macro for writing out the label address in the data section. Macro for generating the interrupt handler for a specific vector, which expands into the text section. Okay. And then ISR thunks. So this is how we do the connection. So the connection is that this data table gets written into an array like here. Syntax, it's an external void pointer to the array name. So that points to the data table that we've generated. Do you follow, Chili? It's just nod. This is a huge, like, rabbit hole of shit we're doing. And I'm hoping it's all just going to click into place. That's the data table. That's the data table, which contains 32 generated functions that we've generated here and here. Okay, and now that's all that's left is when we're looping here, we can set the location to the labels inside of the expanded macros. And now when those macros run, we're going to get the macro number in the RDI parameter, which passes over to the handle fault function, which lands here. And get rid of all of this. That was just all testing stuff. So now we can just literally dump that number into that print log and hope. I don't need that ASM halt because the assembly does that for us. Yeah. This should... You ready? Run. Fault 6. Vector 6. Oh my god, it works. We one-shot it. How awesome is that? Oof, that was beautiful. That was beautiful. Okay, that was really nice. Now, what would be really nice is converting that number to the actual, you know, exception names. I guess we can do that too here, right? I can just do a static map. How do you even define an array of strings in C? Fault names. 32 of them. And then I can just do this as like divide error. Debug exception. Excuse me guys while I copy this list. NMI interrupt. Breakpoint exception. So these are all the possible faults that can happen at the CPU level. Overflow exception. Bound range exceeded. Okay, and then 6. It's a lot of text. Invalid opcode. But this is just like, this is a huge upgrade on our error reporting. And this is exactly what I wanted. I think my next level would be doing a stack trace. That would be cool. Of dumping all the functions that have been ran. And jump to, like, as that exception has occurred. What are we on? 7? Device not available. Eight. Double fault. Coprocessor segment overrun. All right, we're halfway. Invalid TSS exception. Segment not present. Stack fault. Ten, 11, 12, 13. General protection. Fault. Exception. 14 is a page fault. 15 is non-existent. Don't know what 15 is. 16 is an 887. Oh, that's an FPU specific floating point error. Alignment check exception. Machine check exception. 19 is SIMD. Floating point exception. Virtualization exception. Interesting. 21. This is a control protection. And then we've got a generic user-defined interrupts from beyond. Okay, I'll put that in brackets. Let's write %s at the end of that. And let's do a fault names lookup. Wait, so if you do a user... Oh, right, we're only mapping 0 to 32, 0 to 31 in this, aren't we? So Yeah. All right. So now if I run this, there we go. We've got an invalid opcode exception. We now have a textual representation of our faults. Oh my god. We hit a milestone there, and that's because we did this. So if I do int3, generate a different fault type, we've got a breakpoint exception. Well, hey, it's working. Dudes, that is amazing. All right, I think that's good enough to commit right there. IDT. Do we want to call that alt text now printed in log? All right, awesome. Oh, I just realized I committed all this crap. We'll do another commit tonight, it's fine. So, side quest complete. Pretty snazzy. So we will be revisiting this in the future, I'm sure, when we do user space and probably our custom interrupts. So we're only handling 0 to 32 there. We're going to do another macro generated script like this one that handles doing a save and restore of the general registers and then calling into your specific ISR routine. So just to keep it separate in my mind, I'm going to leave this one for now, just handling 0 to 32. And then we'll do 32 to 255 in this one. But yeah, I mean, all I wanted was the text, so I'm super happy with that at the moment. We'll let that concept of macro expanding sit in our brains too. We can think on that. So this brings us on to our next task of the evening, and that is the local APIC timer measurement. So this is about getting every core and its timer initialized, which is slowly bringing us to a point of where we can do user space program scheduling. But that's far off. I think that's going to come after the FAT32 hard drive parsing stuff. Slowly climbing the mountain of OS dev. Okay, I'm just going to go make a tea, take a small 5-minute break, stretch my legs and whatnot, and then we'll begin with the timer code. So I'll be back in about 3 to 5 minutes. BRB. Hello. Boop. Get rid of the text. Hello, Neg. Is that what I call you, by the way? Neg? That's okay. Okay, good. All right. So I just thought what would be a really good exercise to satisfy my thinking about that macro stuff is we can see um, the expanded macro generation in the disassembly, right? So if I dump the kernel image into the assembly, we should be able to find, if I type ISR thunks, IDT emit one interrupt thunk underscore. Perfect. There we go. So that's the expanded version of the macro generation. So we've got the 32 generated labels. Perfect. What assembly is that? It should have output of the preprocessor. This is a dump, object dump. Somewhere down here. Yeah, it's just this. So it's taking the ELF image to an assembly file. What do you think it should be? What are you expecting to see? Okay, did I just change something there? Just white space. Okay. Assembly pro user generate your code has the option to output the macro expansion. Oh, you're saying the actual you're talking about this compilation. You're saying that you can put a flag on here to make it output the assembly for each file. Is that what you're saying? GCC output assembly. You can put -s on the end. Let's have a look. That should have gone into the object folder. I don't think it did. No, I don't think that worked, unless it's got to come before the output file. No, it didn't generate anything new. I can't see, it's just these two files here. Let me just try nuking the folder and nuking the kernel just to regenerate and see if it generates. Nope. Interesting. Yeah, I'll look into that. It sounds like something I want to probably turn on. Oh, you think it's for the NASM line? That's for processing .asm files, though, not the .s files that I'm using. So it's this one that executes for the .s files that we have, which is this here. All right, okay. Side quest for another day. Just remind me in a future stream to do that, and we'll fit it in. So I need to bring up the OS Dev Wiki. So this, again, another one of our knowledge sources. And we're going to be doing or finishing the code inside this LAPIC initialization routine here. So APIC base uint64. All right. Can this OS run last epoch yet? Yeah, sure, dude. We've got GPU drivers, we've got sound drivers. Yeah, we've got it all. I just would not be able to even fathom how much effort would be needed to emulate an x86 Windows game. Like the amount of driver work that would be needed to do that. That's just to think about. It's probably worse than writing an OS. You can't hear me sipping tea, can you? I'd hate for that to be coming down the mic. All right, OS dev time. We're going to be doing the APIC timer. So this guy. I'm just going to give the kernel a kick to see if these timers are still working. So let's give that a run. So 10-second sleep followed by 5-second, 1-second sleeps. But I think I've broken it by turning on some code. So let me comment some stuff out in this section here, which is what appears to be breaking our timers. So try that now. I get so nervous how easy it is to break the interrupt routines. Okay, so the timers are working there. You can see them ticking. So that was a 10-second one followed by 5 1-second timers. So that is fine. Now, when I enable some other code in here, it kills the interrupts. So it's this process again of like turning on bits of code to see what you've actually broken. Let's try. Was it the spurious? You know what? I should not make that first one 10 seconds anymore. And I shouldn't have 5 of them either. Okay. So that has broken the timers, interestingly enough. This one line here, and I'm now going to be asking myself, why would that have done that? Because all we're doing is writing a value to a memory mapped IO register. Missed all the fun. What fun have you missed? I can always take you through what we did if you've missed something. Oh, wait, you were last here when we were wrestling with the HPET, right? So we had a broken HPET, I believe. So the reason that was all broken before was because of volatile, non-volatilely marked struct parameters and incorrect pointer arithmetic when we're writing to mapped IO. The mouse issue, yeah, that's still a problem. It's driving me crazy. Like the interrupts in the entire emulator pause if my mouse is not moving. And I absolutely do not know what that is. The fact that it's staying consistent means that it's not stopping me from continuing, but it's still annoying. But I keep getting situations like I have now. Like I've done something here, and for some godforsaken reason, it stops all of the interrupts on the system. it's not generated a fault. It's just like, you know what? I'm broken, and I'm not telling you why. It's like, oh, really? Thank you so much. Um, all right, so I'm kind of wary when I'm doing memory mapped IO. So the first time I've used this lapic write function, and for some reason when we use it, it's killing the interrupts in the system. So I'm willing to bet it's suffering from the same problems that I had in my HBAT code, where I'm not paying respect to the pointer arithmetic that is occurring. APIC base comes from the model register. Moscow. Okay, so we dump that in the log. So let's start from the beginning. What do we dump as the lapic base? Right, so that is not offset into physical memory, which we are doing here. So what we'll do first is we'll produce a pointer to make this volatile, because it is. So let's cast this to char pointer, and it's this stuff here. So then we'll kprint lapic read, and then we'll print that address. And then we'll do the same for the one below as well. The write. So this is a lapic write on that address, which is the higher offset plus the base plus the offset. Okay. So let's just see if we've got those memory locations correct. So I can see the lapic write at the top here. If I pop open the log, we should be able to see the lapic reads here. Look. And then we've got a lapic write initializing ACPI. Value at that address equals value how is that working actually? Just being a char, that's not gonna. Yeah, I need to cast it to a uint32. And then that'll read 4 bytes off the memory location. Yeah, writing 30. I just realized my mistake here. I've fixed it in the read and then I've got to fix it in the write. So we need to convert this to that. And then we can push the 32-bit value onto that address. So that is probably a bit better than how we had it before. I can't see. Did we just generate a compile error? Is that why? I really need to fix the output so it fails on compile errors. Sometimes it fails on warnings and sometimes it doesn't. It's a bit weird. But yeah, this here is what I'm looking at. So it's generated the BlurOS kernel binary and it's built the image. Thank you, Chili. What have I done? Or are you leaving? Is that a good night? Okay, so I have to be very careful. Like I've got how I'm doing it here is I'm doing decimal calculations and then converting that to a char pointer address and then ultimately to a 4-byte address. But sometimes I do pointer arithmetic and that confuses things even more if I'm doing it differently in different places. So I want to kind of get into a routine where I'm doing the same kind of, style of initializing memory mapped locations. So this set spurious interrupt vector, again, why? Converting just are not needed, I think. Make sure line correct. Yeah, you would be right there because we're generating a decimal value and we can just cast that directly to a uint. There's no need to convert that twice. Yeah, I just really dislike this behavior of I suspect we're doing something bad. And the way the operating system responds is, oh, you're not getting interrupts. Like, you're broken. Go away. It's like, dude, why? Now, I just want to change something in the HPET code. that I think is still causing a problem. So when we do one shot, which enables this here, I'm going to call for enabling interrupts just randomly. I want to see if it's that same issue that I'm having. Hi, Cruz. I know C, yeah, I do. A little bit. I say a little bit. I've been using it for a few months. All right, so it's not the problem. So what's happened? Why is interrupts stopped firing? Why? Actually, I'm going to call this, and then I'm going to call... where is it in my CPU file? CPU H, actually. Are interrupts enabled? Let's just print this. I just want to see if rflags has got the actual interrupt set. Ask me a question about recursive function, sure. Yeah, so the rflags is set, so there's something weird going on. I'm going to not do this HP timer stuff because it might be a HTTP, might be a HPT problem and not everything else, right? So it might be the keyboard might be fine, for example. And no, we're not. We're not getting any fires of interrupts at all, which is awful. It's a system-wide issue. No PS2 interrupts. And there, we're getting keyboard interrupts now, so now we've commented out that code. Everything's working. It's just when I do this LAPIC right. To be honest though, if we think about it, it's the interrupt scheduler, right? The local APIC. So if I'm screwing something up inside of that, it's probably nuking the interrupt system. I wonder if this function's working though. Hold on. I'll know if this works. Have I got it predefined? In LAPIC H. Nope, we do now. So since CPU C, okay, I definitely bring in CPU here. Yeah. I don't know. Can we raise like interrupt 6? Can we force? Yeah, so that interestingly works. Now, if I wasn't writing to the LAPIC correctly, that definitely would not work. Yep, so there's an overflow exception. So the writes are going through fine. So why does it have a problem with me setting the spurious interrupt vector? Okay, we do a cross-reference. And we say, Lyra, what are you doing? So we'll look for that. Got the spelling incorrect there. Configure spurious IRQ. Okay, same register number, I believe. 0F0. Let's double check that. Yep. Oh. Well, we're not doing that, so we're probably trashing the configuration. Let's see if that makes a difference. So we're grabbing the value of this, and then yeah, we're combining it with these values. Bit 8. Enable. Windows calculator to the rescue. Hex code. Oop. Binary. Yeah, so it's turning that same bit on with that value as doing Lyra's bit shift left 8. So that's the same. Oh, but what I'm not doing, again, bit of a silly situation here. We should be ORing this. What if this makes a difference? Casting this to an int32 shouldn't do, right? Because it's just it's the same value. All right, let's see if that works. Where's the VM? Oh, there we go. All right, note to self. If we attempt to trash memory, then the OS has all the right in the world to halt our interrupts. So, one point there to me trashing memory again. I've got to get used to that concept too when dealing with memory mapped locations, is sometimes when we fiddle with bits in those locations, we do want to get a read on the existing config on that register and then make our changes. And again, I think that's specific to implementation. So like checking the documentation for this specific, the local APIC behavior. And it's probably recommended that we do this. So let's just save that call there. Right, perfect. So we're over that problem now. So now we're into the timer stuff. So now we're into the good stuff. So I'm going to enable this stuff, which I need to cross-check with the OS dev logic in a second. This is where we're up to. This is like... Right, perfect. So interrupt still happy. Everything is going to plan. So now, if we check our OS dev chap over here, we need a block of logic at the bottom that tells us what we're going to be doing and why. Here we are, start timer. So we tell the APIC timer to use divider 16. We prepare the pit to sleep for 10 milliseconds, which we can do with the HPET timer. We set the APIC init counter to -1. We perform the sleep. We stop the timer. Now we know how often the APIC timer is ticked in 10 milliseconds, ticks in 10 milliseconds, blah, blah, blah. Why do we store that though? I bet library is storing that on the CPU context or the CPU local struct. Because that's like the timer ticks. But for now, I guess we can just dump the location. Like, we're just dealing with the bootstrap processor still, so it doesn't matter for now. All right, so let's cross-reference this process. And let's see if we can get this going. Reset the timer, so disable it. Timer div, 03, it sets it to 16. Init count sets to -1. Ooh, good song. This is a pumper. All right, so we're here. Now we're going to perform the sleep. So this is where we're going to lean on the HPET timer for 10 milliseconds. So we need to bring that in up here. LAPIC counter, so we're dumping the LAPIC read. Stop the APIC timer, so we're masking the register LV timer. Wait, we need to enable it though. What's this masked value? Up the top, I think. What are you being set to, my friend? We don't have a reference to that value. How about the assembly code? Software enable, APIC timer to interrupt, set up divide, initialize, pit one-shot mode. Where's the enable? Here. APIC disable. Word. Map the APIC timer to an interrupt and by that enable it in one-shot mode. Why are we writing the value 32 to that? Why, oh why? So the disable is on a different bit, is what this is telling me. Anybody know off the top of your head what OX100 is? 256. I knew that. All right. Oh, the music's gone serious now. Serious business, guys, now. We're just at the bit where we're measuring the timer. So we disable the timer here, but we don't want to do that. We want to... I mean, we can disable the timer, set the div, set the initial. It's here that I need to enable it, though. So the enable is this guy. Or was it enabled when we enabled the APIC? Okay, let's try this. Let's just move this disable after the sleep. And then we'll... This is debugging code for capturing the counter value. So this double read should get us the same value because it's disabled, right? So let's see. Do we get... Got a page fault. Why am I getting a page fault? Did I leave that code in, or is that a proper page fault? Full stack 25 years. Hi. Wait, are you just reading my bio? I think that's what I put in my bio, isn't it? I can't remember. Yeah, welcome, OG. Let me just comment this code block out. I can't remember if we've left some test code in the kernel C. No, we didn't. So where are we page faulting? All right, so it is what we introduced. All right, cool. Let's find the line. Is it before we sleep? Assembly is Chinese. It was for me. But when you spend time with it, it's not that bad at all. Okay, it's not there. That's all absolutely fine. Did we get the HEPT sleep and the LAPIC right? Double it up there. All right, we're page faulting. So why are we page faulting? Did the sleep occur? I don't think it's the HPT. That would be wild. Oh, it did. What on earth? Wait. Huh. I've got to be careful, like when I'm writing debugging code. We're still page faulting. Right, okay. Somebody isn't happy in there now. But why? It's got nothing to do with the LAPIC. Like, what have I changed? All I've done is wrote some memory registers for the local APIC, and now the HPT is broken. Fun stuff. Reset, disable. I feel like putting a debug switch in here. We want one in the reset function. And in the disable function. Okay. See, that's where a stack trace would really help. Okay, so it's after the disable, which we're not writing new lines after all of that. How bad of me. Oh, we'll put one in enable as well. See if it got that far. So it's page faulting on the HPT disable. Really? Not a single night of OS dev that doesn't throw me into some wild, unknown, like WTF. That takes some crazy debugging. Yeah, so it's page faulting when I'm trying to write the regs, but That wouldn't have changed. What on earth? What a long disconnect. Oh, sorry, you've missed us deep diving into a strange bug that we're getting. Wait, why? Messing about with the APIC wouldn't have done anything like this. It's got nothing to do with memory mapping stuff. Um, I do want to disable links in the chat, actually. Can I block terms, printed terms, ban evasion, block hyperlinks? There we go. Is your timer restored or not yet? So we're getting a weird bug that when we're asking the high performance timer to sleep, it's generating a page fault exception now, which is bizarre. So we're getting a random page fault deep inside of the disable function, which is just a register write, a single register write. So I'm going to just confirm that this address has not changed. So I'm just going to write the location of that. Oh, it's been nulled. Wow. What? Oh, it's null because, oh, you idiot. Just when I'm getting worried that I've broken something, like, you need the timers before you initialize the LAPIC, right? So order here is important. So I'm going to do this as early as I can, just after the memory manager. So all of this CPU LAPIC stuff, yeah, that's all it was. Oh my god, I can't believe it's all it was. Let's just get rid of that. Define. Okay. All right, so we can just re-enable all of this now and then see if we're back to now getting two matching LAPIC counters after we've disabled the timer. Bit curious though. I want to check this in Lyra. So timer calibrate. Okay, it's taking its sweet time doing that. Right, timer stop, initialize the pit. LAPIC timer vector mast. timer div 0. Okay, we're using a different divider, but that's fine. Samples initial, APIC write, timer init count, samples. Sets the count to -1. And does that right before the read. So the timer is running. And we're just setting that to 0, then quickly sleeping and then telling the timer to stop. So that mechanism there is start at 0, wait 10 milliseconds, disable, and then we'll get a count. All right, let's check the logs. Still faulting. Uh-oh, did I get a compile error? Nope. Okay, where are we faulting now? Are we still faulting on the HPT sleep? Is that the problem? Did I save the change to kernel C? Lapic init, hpet init. Okay, that's all good. Wait, so why is the HPT timer faulting on initialize? What have I assumed might be working that it's not online? Oh, I know what. The IO APIC. Maybe. ISO list. Thanks for the follow, Ubil. This is fine. I think this is just a problem with the order of initialization. So the HPT10 wants to call IO APIC redirect IOQ. To do that, ISO list. That's not populated until the ACPI has been passed. So this is even before initializing timers. So that's initializing state from the ACPI. Now that we have that, the HPT timer can initialize because it's got the ISO list. Yep, okay. Order matters, friends. Order matters. All right. Here we go. Okay, now. Sweet. We are initialized, and now we need to check, did we get the matching values that I think we should have got from the initialization? So let's find it. Where is it? Where is it? Lapic counter. Oh, -110, -991448. Why would that? APIC counter. Timer current. Disable. Stop the timer. APIC disable. APIC plus timer. So it's going to the timer register, which is what we are. Disabling, we're using that flag value. Okay. That checks out. Wait, that's the APIC disable. That's not the timer disable. Curious. Why? Yeah, that's the problem. Wait, is it? Is that the problem? 0320, 0320, same addresses. So why didn't it stop? You know what? It kind of doesn't matter that it does stop, because all we want to do is snapshot the value, right? Now, if we could do this 3 times, and we should be getting the same similar values. That's what this logically needs to do. So yeah, val, you are redefined, sure. That's not good. Um, hmm. Let's try and what was the address? 320, the timer. The value APIC disable. Boop. I bet the timer needs to be disabled before we can reset the counter. So I'm gonna just do that just in case. So the first two look very similar, but the third one finishes a lot quicker. Let's put this in a for loop. Let's get like an average of like 10 runs, right? Printing an unsigned value with D. Oh, you're right. Let me just do LU. Well spotted. Right, so let's do 10 runs, right? It should be very similar. Oh, there we go. That's what we were after. Well spotted on the printing. I think that was throwing me off. But that's huge. Okay, so that checks out. And then just to satisfy my knowledge too, if I double the sleep, let's just see if we get double the values. And are they all similar? Kind of. Curious. 5 milliseconds? Half the time? No, they're the same. What is going on? One millisecond. Hold on. I just want to check something. It shouldn't matter. But for my own satisfaction. Okay. 1,000. A 1 second sleep between those. Something not right. Consort the let's count it down from -1, make it positive. We divided it down by 16. Uh, Val really meant to be a uint 32. From the read, yeah, it's a 32-bit read from that register. It's kind of why I casted it to a 64. I think what's just really thrown me off is how the counter is not resetting. Like if I did, I don't know, if I did something stupid like 10 times I, so it's staggered, and we should have radically different timer values per iteration. So that timer counter is counting down. It's not resetting when we send in the LAPIC write. This line here, that's not happening. Global enable the APIC, software enable, map spurious interrupt to a dummy ISR, map the APIC timer. See, we don't do this. Initialize to pit channel 2 in one-shot mode. Oh, that's using the pit timer. Set divider. So we're missing this line here. I don't know if it makes a difference. We can try adding this. Which is here. So it's at the timer register and it's setting the value 32. Let's just see if that makes a difference. It might. It's a 64-bit system. Nope. I'm just going to set 0 here. I don't want to set it to the max value. I want to check something. Interesting. If I set 1. Nothing. Curious. Curious. Curious, curious. Timer div comes after. doesn't matter, right? You don't want to be setting that every time. I mean, we can, but it shouldn't matter. They do it last too after they've called all of this stuff. I guess as long as you set that before the read. I'm gonna set the timer div to 0. Do I get different numbers? So that's going from 429 to 424. And that's going from 429 to 428. Is that kind of, though, the behavior that we're after? Because they do... Hold on. Set one shot. Reset the APIC timer to -1. Set the init CNT to what's in EBX. EBX has been set to FF again. Now wait until the pit timer reaches 0. Get the current counter value from timer current. Okay. If it's counted down from -1, make it positive. We use the divide value different than 1, so now we have to multiply the result by 16. Moreover, the pit did not wait a whole second, only a fraction, so multiply by that too. EAX now holds the CPU bus frequency. Now calculate timer value of your choice. This means that tasks will be preempted 1,000 times in a second. 100 is popular too. That doesn't make sense to me, what that's saying. Tasks will be preempted 1,000 times in a second. By tasks, does it mean when you're using the TSS, for example? When you're asking it to task switch, is it checking for that 1,000 times per second? Is that what this whole timer thing is? It's not about the timer in my mind, like a stopwatch, you know? While Lapic read reg timer current count is not equal to 0, why would you do a while loop on that? Int masked. I think that's interrupt masking. Now we know how often the APIC timer is ticked in 10 milliseconds. Tick in 10 milliseconds equals this minus a read on the current counter. All right, let's put this. Let's do a one-shot thing. So disable. This, I'm unsure we need. Okay, sleep for 10 milliseconds. We set the timer in it reg to this thing. We sleep. The div comes up here. Sleep for 10 millis. We disable the timer. Whoops. Hold on, let me check something. Whoops. 32 decimal. Bit 6. So, it's on the internet somewhere. It's the same value. Okay. A random confirmation there. So this is that same value minus a read on the timer current and then sets a periodic timer. Ticks. You start the timer, then write to it, then you need to enable it again. That's what I'm confused about. So and I'll show you why I'm confused about it in a second. I think even though I'd call this disable instruction here, the timer's still ticking. And you'll see that in this log. Show you. If I get 0 ticks, then I know it's 100% disabled. But I feel like it's not disabling. Where are the ticks? There you go. 940,000 ticks. Like, it doesn't make any sense, does it? You're looking at it logically here and you're saying disable the timer, set the divider, set the counter, sleep, disable again, and then you do a read on the counter and you've got something in there. I mean, if I put it in exactly how the OS dev tells me to, write 32, and then after it's got that ticks in 10, it wants us to write with a periodic flag, which I don't believe. Where did that come from? Oh, yeah. I mean, we're going to see it firing down IRQ0 anyway, right? After I set this up, so let's see if it works. It might be that the disable and the enable is for the interrupts. And the actual counters that we're thinking about, they're just continuously counting. Like, that's what happens in the HPET as well. Like, the counters are just constantly firing. It's just the interrupt generation that's suppressed. So I think this is suppressing interrupts, if anything, and then this turns them on here. Maybe? We need to find the documentation and software manual's got a section on it actually, which is nice. Thank you for the follow, Sherlock. So the APIC's in here. If we can just get a view of what's happening in that timer byte memory, that will help. I want to see local APIC state ID, version register. Just try, see if I can find a diagram for the bits. Register address map. So they're the address locations. Yep, so these are the address locations for the registers. I need a bit breakdown. Status and location. In the base MSR bit, functions are described below. Well, that's not the LAPIC timers, is it? That's just the APIC ID stuff. Yeah, that's not timer stuff. There's another link here. Talks about the IO APIC, physical-logical stuff, local APIC initialization. Yeah, it's not timer stuff, so that's disappointing. To measure the CPU's bus speed, you'd see how many times the APIC timer's count is decreased over a fixed time delay. Oh, that's why we saw the counter decreasing when we snapshotted the value into the log. It wasn't that we were setting that counter. Yeah, so it looks like here too, telling the local APIC to use the int vector, set it to one-shot mode, and enable it. So it's like when you write to that register, it enables the timer. It's kind of a bug in this logic too, that it's setting this divider to 16, and it's not multiplying the number like it does in the assembly code here. So if we set the divider to 0, that should save us having to do a multiplication on the value. Right, so that we think is enabling one-shot mode here. Read the timer, stop the timer, get the ticks. And then start writing to the timer register again with this periodic mode, which is that value. And then for some reason we're setting the timer div again. Like, why? And then we're setting this to ticks in 10 seconds, milliseconds. And that should give us an interrupt on IRQ0. Are we listening on IRQ0? I thought the HPT. Oh, uh-oh. Uh-oh. Okay, that is going to cause us some problems. If I... Let's just get... let's get a log in here. Make sure we're not interrupting the same ISR as the HPT. All right, well, let's fire it. Let's see. All right, we're getting ticks. As you can see, it's going crazy because we're writing off on that interrupt. Which is wild. Oh, I've got an interesting problem now, though. The HPET listens for its events on IRQ0, but here I could have enabled. I'm going to test something. I'm going to keep that tick in. I'm going to halt the processor here and see if those interrupts are firing. Okay, so they're not firing down IRQ0, right? So my point there is that the only thing that should be firing on that interrupt vector is the HPET. Is that the vector number? No, it can't be. We need to find documentation of how to override the IRQ that this time is firing on. But as far as I'm concerned, the HPET has no problem there firing for 10 milliseconds. Actually, we confirmed that before when we asked it to, like if I asked it to do it over 5 seconds, we should see a huge delay in the boot time. If we don't, then yeah, so and now we're getting a tick, look, which is the LAPIC ticking. Interesting. Why was it firing so aggressively before? This doesn't make any sense, man. Why would sleeping the HPET timer on a different value affect the ticks on the LAPIC? Oh, because of course it would. Also, this needs to be 0. That might be an issue. Now, okay, one more test we can do. You write 10 milliseconds of value in it at the end. Yeah. So this whole routine here, grab this. I can kind of see now why we kind of want this in its own. what I want to test for here is if this calculation is the same of dumping how many ticks there are in that measurement, then there should be a very, very close value if we ask it to initialize that timer 10 times, right? So I'm saying do 10 measurements. So we should get LAPIC ticks to be very, very similar. Before we were trying to do that with the counter, which we know is just an ever decreasing number. So we couldn't do that test properly. But this one, this one should report similar values. Oh God, I need to get rid of that ticking value here. I really hate that this is used for the HPET. Yeah, I think there's a lot to unpack here. So look at how wild those measurements are. That doesn't make any sense. You can't get to one measurement there of 31 million and then 11 million. Like that difference is insane. So, oh boy. It kind of doesn't make any sense either in this whole Lyra source code. Like, why is it reading the current timer? On a while loop and then instantly breaking? Kind of doing a different math equation though. It's measuring the ticks on the pit. Where's that divine? So that frequency, that's a frequency value of the pit timer. Huh. Timer stop, initialize the pit, which isn't really a pit, it's doing timer stuff. Sets the divider to 0, resets the pit. Whatever that measurement is on the pit, I've no idea. Initial tick, get current count. Final tick, get current count. But you did no waiting. You waited for that kind of number of samples? Is that the wait? Line 82. Yeah, I don't understand though how that's related to this samples value. So it's just, I mean, let's just pretend that's whatever number, like the decimal of that is. The amount of ticks that's happening on the LAPIC timer. Is that not equal to 0? That's mind-boggling because timer div 0. Like how have they seen that value at 0 when we never see it at 0? Huh, that actually fired the interrupt. Got so many different versions of logic that I'm comparing against, you know? Like, it's quite disturbing that this code here is quite different to what's happening in the assembly code here. So it's like, which setup do you use, you know? Do I just keep trying one till it works? Yeah, I've got the assembly version. I've got this pseudo code here for the C. And then I've got Lyra's example. What would be very helpful is the LAPIC timer reference somewhere. You know what? It might be. You know what we haven't checked? Part 1 manual has a chapter on the APIC in 3A. Architecture Software Manual, Volume 1 Basic Architecture. System Programming Guides for Thermal and Power Management, features multi performance monitoring. Perhaps generate assembly from your C and compare that. I think, yeah, it's the same manual that we were looking at. The problem with this manual, it doesn't have timer stuff in it. I'm lying. APIC timer. All right. Let's see what the official Intel doc has to say. The timer is set up by programming 4 registers: the divide configuration register, fig 11 till 10, the initial count, and the current count registers, and the local vector table timer register. If CPU ID leaf 06H, the processor's APIC timer runs at a constant rate regardless of a P state transitions, and it continues to run at the same rate in deep C states. The APIC timer may temporarily stop while the processor is in deep sea states or during transitions caused by enhanced Intel speedstep technology. That sounds fun. The APIC timer frequency will be the processor's bus clock or core crystal clock frequency when TSC, core crystal clock ratio, is enumerated in CPU ID leaf OX15, divided by the value specified in the divide configuration register. The APIC timer frequency will be the processor's bus clock. The timer can be configured through the timer LVT entry for one-shot or periodic operation. In one-shot mode, the timer is started by programming its initial count register. There you go. So it starts by setting initial count. So that fires the timer. Go! The initial count value is then copied into the current count register and countdown begins. Okay, that's important to know, the state of the registers. So we set a massive number, and on start, that gets copied into the current count, begins to count down. After the timer reaches 0, a timer interrupt is generated, and the timer remains at its 0 value until reprogrammed. Lyra, while timer current is not equal to 0, it's waiting for the countdown. All right, so we've got some various things here being confirmed, which is nice. After the timer reaches 0, a timer interrupt is generated, the timer remains at 0. Yep. Okay, in periodic mode, the timer is started by writing to the initial count register, as in one-shot mode, and the value written is copied into the current count register, which counts down. The current count register is automatically reloaded from the initial count register when the count reaches 0 and a timer interrupt is generated. And the countdown is repeated. If during the countdown process the initial count register is set, counting will restart using the new initial count value. The initial count register is a read-write register. The current count register is read-only. So that's the divider that we've seen various solutions setting for God knows why. Initial count, current count, address locations, lovely. A write of 0 to the initial count register effectively stops the local APIC timer. Ooh. In both one-shot and periodic mode. So, so this is important. Writing 0 kills the timer. Writing any other value starts the timer. Okay. The LVT timer register determines the vector number that is delivered to the processor with the timer interrupt that is generated when the timer count reaches 0. The mask flag in the LVT timer register can be used to mask the timer interrupt. Changing the mode of the APIC timer from one-shot to periodic or vice versa by writing to the timer LVT entry does not start the timer. So there was a lie, I believe, on the OS Dev Wiki. in a comment about the timer was going to start when we set the interrupt. Okay, to start the timer, it's necessary to write the initial count register as described above. Again, confirming, you can only start the timer by writing to the initial count register. Okay, thank you. My head is now much more clearer. So the mode of operation of the local APIC timer is determined by the LVT timer register. Specifically, the mode is determined by bit 17 of the register. The mode is determined by bits 18 to 17, see figure 11.8. If CPU deadline bit 0, bit 18 the register is reserved. What? It's telling me there the result from CPU ID tells me whether it's a 1-bit or 2-bit value. No, the mode is determined by bits 18 and 17. Supported timer modes are given in table 11.12. Okay, one-shot mode, periodic mode, deadline mode, program target value, reserved. LVT. Okay. TSA deadline mode allows software to use a local APIC timer to signal an interrupt at an absolute time. In deadline mode, writes to the initial count register ignored. And the current count register always reads 0. Instead, timer behavior is controlled using the deadline MSR. The deadline MSR is a per logical process model service register that specifies a time at which a timer interrupt should occur. Writing a non-zero value arms the timer. An interrupt is generated when the logical processor's timestamp counter exceeds or equals or exceeds the target value. All right, that sounds like a different way of using the timer completely. It depends on the model service register. So detect support from the leaf on the CPU ID. Select the deadline mode, program the MSR, generates an interrupt, rearm the timer by repeating step 3. Okay, so that is actually all of its documentation. Interesting. It's literally just a one-pager. All right, now we know. Now we know. So disabling the timer is putting 0 in that thing there. Can we just like record this in a bunch of functions so we know. So setting that to 0 stops the timer. And this here turns off the LAPIC. Wait, LVT timer, disable mask. I don't believe we found documentation on that mask level, did we? Interrupt input pin polarity vector. Mask, not masked. Where are you pointing to? Yeah, it was definitely helpful because it's confirmed like the absolute truth of what's going on with those registers and what it means to disable and fire the timer. It makes no sense to do anything with these timer dividers like that we've taken from the OS wiki. Like, just set that once and that's it, you know? Off it goes. I want to know what that LVT timer's doing, though. Is it this here, local vector table? Is this what I'm this exactly what I'm looking at here? What bit is the value 32? Bit 5. Vector. Oh, 8 bits for your vector number. God, I can't see the wood for the trees sometimes. Right, so the diagram we're looking at is the LVT timer register. The first 8 bits of that is the vector that the timer is going to use. Okay. Which is why we've written the value 32 to that register. Because we're accepting that on, if we go back to the IDT, we've registered the timer vector on 32. So if I wanted to, I could put it on 33 because 32 is being taken up by the HPET. So I could create another vector for the LAPIC timer, right? So that's that sorted. And then what's 8 to 11 doing? Oh, is that reserved? Oh, it is. It's reserved. So when it's dark, it's a reserved area. So 8 to 11 is reserved. Bit 12. What's bit 12 doing? Bit 12. I can't see what that's doing. What might help a little? It seemed to have been starred out for some reason, what you said there. 13 to 15 is reserved. 16. '17, 18 timer mode. Oh, there we go. So yeah, bit 17 and 18 timer mode. I'm not sure what bit 16 is doing. Bit 12 is delivery status. Oh. Sorry, I missed that. The diagram's a bit weird. Send pending. Oh, so that's a that's what assists the interrupt firing. There's always a bit somewhere that gets flagged when an interrupt's ready to send, and then there's probably a bit that stays high whilst the interrupt is in progress and then gets cleared when it comes back. I've noticed the HPT timer did that. Had an interrupt status register. That delivery mode is interesting. Which I think is active. I know it shows reserved here, but oh, 16 is this masked here, which is the enable disable mask, right? What's the value at bit 16? Does anyone know? I always have to, how do I even get that? 32 bits. Hold fire here. 8, 16, 24, 32. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16. Decimal. Binary. Ah. So that mask, you know, we've seen that number before, right? Boom. So when we write that, we disable. One is masked. Okay. But we never flip that to 0, though. That's the interesting thing, right? Do we not? Oh, we do. Don't forget this is a single 32-bit register, so when we write multiple times to that register, like here we're writing it's masked. Okay, it's masked. And then we're hitting this value. And then we're going 32, right? So I've set the vector. The mask is now unset. And off it goes. And it's in one-shot mode because we've not written that bit there at bit 17 and 18. So we get a one-shot timer. The second that gets written there, which actually this isn't actually a true statement now. I understand now why the OS dev had that comment. It wasn't lying. Like that literally just disables the timer until you do another timer right. In one-shot mode. And 32 is the vector. There we go. Beautiful documentation. We're getting there, guys. You've got to be like Sherlock Holmes in reading this stuff so you know exactly what's changing under what circumstance. But it's so satisfying to get, a grip on what it is you're dealing with. It feels so nice to understand that vector from this diagram. That's what I was after at the beginning. I was like, what is this, LVT timer? I want to know what's going on inside that bit structure. And bingo, right? There it is. And I like to put all these comments in because what I want this Git repo to serve, and what I see lacking from a lot of open source operating systems that are being developed, is the commenting is lacking a lot. Like people are throwing code into their operating system without any reasoning, any explanation of what's happening. And of course, the developer can always go back and look at documentation, but I'd like to transfer that knowledge to the code and why it looks the way it looks, Because sometimes you can miss looking at that thinking, oh, I've written the disable, bit, and then suddenly I'm writing to the register again, the value 32, or what does that do? Yeah. It's kind of nice though how that write kind of like just set the vector and off it goes. Set the count to -1, so that starts the counter from the topmost value. We sleep for 10 seconds. We disable the timer, which by the way, I don't think it does, right? Didn't we already say that when we disable the timer, when we mask it, it doesn't stop the current timer counting? It's just masking the interrupts. So we slept for 10 seconds. Yeah, why would we ask it to fire on the interrupts and then disable interrupts? Like, why would we do that? Just to prove to you guys what I'm thinking about, right? Of why this is a bit weird. So I'm going to purposely lock the process here in a while loop. I'll show you why. LU. we're going to read the timer. Oop. So I've disabled the timer, and I'm just going to infinitely print what's on that timer thingy. Initialize, set to 0. It's in periodic mode. You need to stop it from firing again. Not at this. This right here has only set the disable bit. So the whole thing's masked, right? And what I want to show you in the log is how that timer is constantly ticking. Right, it's ticking it. It's not set, so we need to. Okay, we need to fire this command first. Bear in mind there, we haven't touched the LVT timer register. It's still on disable. And there goes the timer. You're getting timer values counting down, but you're not getting the interrupts. So there we go. Goes to 0. Boom. Oops. So I want to keep the timer masked. I don't want to have interrupts firing. Do I? No, we don't. All right, so that checks out. It's all falling into place slowly. Clear that line for now. So that starts the timer. Sleeps for 10, disables. Don't need that disable. Oh, do you know what I haven't tested though? What if, okay, let me just wind back. There's one more test I want to do. When I set that, okay, I'm going to print the timer at the beginning of this while loop. And then I'm going to write 0 here, which should stop the timer at its current value. I want to see if it pauses on the value. No, it goes to 0. Huh. All right, that's fine. Okay. This was masked all the time in one-shot mode, 32 is the vector for the interrupt. Don't want that. Set the count to -1. That stays. Wait, did I just murder that? Comment belongs down here on this call here. So ticks in 10 milliseconds. It's a 10 millisecond interrupt. Right. That's it. It's solved. We've measured how many ticks there are in 10 milliseconds. And that's what we're setting in the periodic timer. So what I'm asking for there is a 10 millisecond interrupt. Line 86. Control your last counter value depending to divider. Yes, so that's why I'm setting that to 0, so I don't have to worry about dividing or timesing any numbers. I'm just doing a small 10 millisecond measure, and whatever that comes back as, I'm putting back into a periodic timer, and then I'm getting a fire every 10 milliseconds. Now, what I want to test is if I put this on vector 35, which goes on here as well. LVT timer disable. Oh, wait, do I want to call this here? No, I don't. Disable interrupts. Start the timer. Don't want that. Read the timer. Like that's the same, right? Let me times this by 100 to get it in seconds. And then I just want to put a log line. So we've got interrupt 35 there. I just want to check. I just want to check if we've got control over that vector. I'm hoping to God we have. It should work like this. And then that's everything. I'll just overwrite this one. Uh, 35 Lapid timer vector, and then when we initialize the gates, push this here for now. It won't stay here long term, but so that's the Lapic timer tick. Now, because this is a Lapic timer, you've got to acknowledge, you've got to save, and you've got to restore. And you've got an unreachable code section here. So all that stuff comes in. I think line 6 is important. If your counter reaches 0 during 10 milliseconds, it'll stay 0, while your other 10 milliseconds still running at 0 divided by 2, your ticks. If your counter reaches 0 during 10 milliseconds, which it won't, like the measurement of 10 milliseconds here, there's no way that time is going to get down from its max value to 0. Right, let's just see if this works though, because this will be amazing if it does. Page fault. Why am I page faulting? What did I do? Who's page faulting? Why? Why are you page faulting? What did we get up to? LAPIC base, LAPIC ID version, MSR, fault. Yo, things were going so well. What did I do to cause the fault? I've not touched any addresses or anything. I didn't change the order in the kernel. I set the vector in the IDT. Please tell me that that's not a taken vector, that's firing some random interrupts on. Yeah. How? How would we know this? Like, who's using that vector? Hello? Get off my user vector, dude. Oh, I don't think that's the problem either, though. Is it? ISR save restore, that's not. LAPIC end of instruction. Kprint F doesn't die. So weird. Page fault. You only in it too. Yeah, there's only 32 fault handlers, but I'm setting the gate here for that vector manually. And the only thing that's firing on that vector is what we've set in the LAPIC. We should use that LAPIC vector define here. Okay. Yeah, what's kind of, I've got multiple things running around in my head here of what that could be faulting on. And it's obviously something happening inside of here. Let me just check if it is the terminal being an idiot. No. ISR save and restore doesn't really care. LAPIC end of instruction. Oh. LAPIC write address APIC base. It's going to be 0. Why would that be firing though? So early. Just to test this, by the way, I'm going to comment that out, and it's going to run now. I know it will. No, I'm lying to myself. Oh, what is it then? What is it? IREQ. What if we leave it empty? What if it's this stuff? The ISR. Okay, that's not. We've broken things. The LAPIC isn't even initializing there. Do we have a faulty build? No, we don't. Mr. LAPIC, why are you not initializing? Hmm. APIC base gets set way on the initialize. Okay, but we know it's not that. PS2 initialized. Servicing hardware 2D. There's no exceptions. Why is the LAPIC not firing? Let's just wind this back then. We're not setting the LAPIC timer vector now. That shouldn't matter. General protection fault. Something's really gone weird. What have I screwed up, man? Why is it jumped to PS2 initialize there? Like there's something really gone weird. It's finished the LAPIC init, it's jumped to PS2 initialize, but the LAPIC init hasn't fired the timer inits. Oh, it could have done. Actually, could have done. Silly me. Right, so general protection fault there is because it's firing the interrupt and it's not being handled. It's in a delayed. It is running this code, which by the way doesn't need to do it 10 times anymore. So it's when it's set the vector here. So 45, and then in here, register 45 against that method. Acknowledge the LAPIC. Restore. Yeah, so as long as we're doing all of that stuff, it shouldn't crash. That's a really fast page fault, though. Like, where did it page fault so fast there? All right, some logs right here. So, setting climber vector. I am going to set that to 0 to disable the timer. Wait, I might need this. I'm going to put a time stop here. I think that's what's screwing me up whilst I'm setting stuff. Page fault. I need to see if I'm actually getting this far. No. Interesting. Is it somewhere in here? Measuring. It's in measuring. A page faulted in measuring. What? Is it after that? Are we dying in HPET again? I bet we are. Something's not initialized for the HPET and it doesn't like it. Right. Page faulting inside the HPET. Why though? Everything you need is online. Let's turn debug mode back on for the HPET. I'm glad I left this in. Good job, me. Future me is proud. So we hit one shot, reset, disable, enable. Enable, enable, enable. Okay. Which is this here? Are we dying here? I think there's a debugging lesson to be learned here once I've solved this. Enabled. But no. Yeah, we faulted there. Why though? Why? What does that address look like? Last time it was a weird address we were suddenly working with. Yeah, it looks healthy. That looks healthy indeed. Who's calling enable? It's after one shot. One shot's called by sleep. Okay, did we get this far? One shot finished. Well, you're not called by anywhere but here. Da 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 da. Sleep. Something really weird going on here. I'm suspecting. Why would it page fault after the enable? What on earth is happening? What on earth is happening? Like the only thing that could be throwing this off is an interrupt, an ISR. What am I coding? An operating system, buddy. We're working on an operating system. Cold tea, yum. So, God, how do we even get past this? Because the HPT depends on interrupts. What changed in the last 30 minutes that caused this to misbehave so badly? Like the only thing I fast forwarded on doing since we were debugging the timing stuff. Disable interrupts. Start the timer. Sleep for 10 milliseconds. Read the current timer. Didn't we have a line? No. That was overridden. Huh. What changed is that we switched to another vector. Yeah, true. If I put this back to 32... Faulting. And then this wasn't even being registered in the gate, right? Like, I can just disable that because it wasn't there before. And we're still faulting. Are we missing a command off one of the LPICs maybe? Like, it's in a disabled state, but does it matter? Like, didn't we have before... this? Is this the problem? Oh man, this is killing me. What on earth is causing this? What if I don't initialize the timer? Everything's happy. So something we're doing down in the timer is screwing us up, really. Let's just replace that with what's happening above. Stop the timer. Oh. Volatile, return address inline. Let me just disable this unmasking. All right, so we know now it's definitely something to do with how those interrupts are firing. Let's set that timer. Or do we set this first? Disabled's been written. The vector has been cleared. Page faults. What code are you? 14. Okay. Period timer, vector 32. The vector 32 in the IDT. Checks out. Okay. So we added this. We registered it here. Handle timer. We put this function here. Yeah, why does it page fault when we activate that vector number? We also didn't times that by 100 before. Still page faulting. All right, still screwy. I just want to verify this hex number in the calc. Let's just cross-reference that with this. Zero to 3. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So it's on 01, set to periodic. Right. Maybe you are print its 45 vector string. Maybe you are print its 45 vector string. We've taken out the 45 vector. It's not firing on the vector 45 now. We've set it to 32. Line 89. Yep. Let me just not set that. Now, not setting that means that nobody set it. So what is that defaulting to, I wonder? Still page faulting. Why is it being an asshole? Unused variable. Page fault. You know what I think is the problem? I think I know what the problem is. I think I know. We had this at the beginning. Also, where's the div gone? Did we get rid of this? I've got a feeling like we removed those and they must. No, we're still faulting. Woo, this is fun. Maybe I didn't save the IDT file. Let's nuke everything. Let's kill those logs off. We'll kill the kernel image. And we'll kill all the lib stuff. All right. Rebuild, rerun. Yeah. Oh man, this hurts. This hurts. When you get a page fault, so doesn't it give you the RIP? Um, da 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 dum. Like, can't I see where it blew up on? Like the instruction. If I could see the exact assembly instruction that was causing the page fault, that might give me a better interaction with the debugging. How would I do that? I just don't get how it was working 30 minutes ago. Ah, what would be a good debugging strategy here? I could clear interrupts. No. I'm going to log exactly when we do a write. Okay, those addresses all look super healthy. Did we get down to here? I can't remember. Um, okay. It's like it's as soon as we unleash the vector, the second we tell it to start sending interrupts, it goes crazy. Maybe that above that? I don't know. Oh, I know what we could do. I think I know what we can do here. Wait, where's the unmasking line? Wait a minute. Wait a minute. Oh, I can't type now. Yeah, it's not getting out of the. It's not getting out of the HTT. 'Cause, 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 ' Whoa. Yeah, for some reason, it's dying inside of the HPT sleep. Wait until the ISR fires. The ISR is not been disturbed. You are that's 0 to 31. The IDT 0 to 31. The timer's back on 32. Handle timer is the handler. ISR, you're doing nothing important. ACK doesn't really do anything. LAPIC end of instruction. ISR restore. Hmm. Let's see where that interrupt. Wow, this has gone really slow. You know what I'm gonna do? I'm gonna reboot the OS. The good old rebooty. Um, hmm. I'm running out of steam, guys. My brain juice is depleting. Right, we're back. ISRPS missing .note GNU stack implies executable stack. That's a linker warning. Missing note GNU stack section implies executable stack. Don't know what that means. H faulting inside the HPET. What if I lie? Like, what if I turn off? Wait, let's just return here. Let's not even worry about it. Like, just go. So something is screwed up even now because, like, it's crashed. Didn't I have a tick in here before? No, wait. Gosh, what on earth has changed? This is so horrible. The last time I had this problem was I wasn't using proper volatiles. And if I add, let's see, let's add 01 to the build. O2. O0. Possible constraint. What? Function CPU ID. ASM operand 2 probably does not match constraints. Warning is error. Impossible constraint in ASM. AD. AD. Code EBX CX. Possible constraint. Let's do a quick Google on that. Might be runs out of registers. With O on a higher, the SE doesn't do what you expect. It doesn't like one of these parameters. I guess we can't use that here. Oh, I'm out of ideas. I'm going in circles now. I'm going to have to leave it there for the day, I think, and try and unpack it tomorrow. But we went from a good state to a broken state just as we were putting the cherry on the top. So it feels like one step forward, two step backwards. But it was a good stream, like we got the faults coming through an assembly process now. I'm pleased about that, and we've kind of nearly got the LPIC timer working, so it's just a matter of time. So yeah, I'll see you guys tomorrow. I think I'll be streaming, same time, same place, minus 6 hours. And thanks for being here and debugging with me. Thanks, Neg. Git, it's good thinking. Because I do not trust the call it timer whip, because it is. It's not finished. Cool. All right. Thanks, everybody, and I'll see you tomorrow, similar time. Have a lovely evening and a good start to your weeks. And GG's. Goodbye.